Hello and welcome to my lab report video for Lab 3. The objective of this lab was to use the momentum principle to find the mass of a black hole. To do this, I was given 4 pieces of information. First, the position of the star in meters for 1,095 days during its orbit around a black hole. Second, the position of the black hole in meters. Third, the time step or delta t, which was 86,400 seconds, which is approximately 1 day. And lastly, the mass of the star. For this lab, I assumed that the gravitational force from the black hole was the only force acting on the star. Using these, I found the mass of the black hole to be about 4.8 times 10 to the 31st kilograms. To calculate the mass of the black hole, I used the momentum principle. To begin, I used the position points of the star to find the star's displacement during each time step. Then, I divided the displacement of the star by delta t to find the velocity of the star at each time step. Using the change in velocity and its mass, I was then able to find the star's momentum at each time step along its path. Next, I found the rate of the change in momentum by dividing the change in momentum by delta t. Since we know that the rate of change of the star's momentum is equal to its net force, I could then calculate the mass of the star using this equation. In this equation, I calculated the net force for each time step along the star's path in newtons, and r to be the distance in meters between the star and the black hole at each time step. For g, I used the gravitational constant 6.67 meters cubed over kilograms times seconds squared. And lastly, I plugged in the mass of the star as 5.3139 times 10 to the 27th kilograms. This gave me a mass for each time step. I then computed the final mass of the black hole to be the average of the masses for each time step. I found the mass of the black hole, as I said before, to be about 4.8 times 10 to the 31st kilograms. The net force of the star is a vector that is made up of 2 other vectors. One of these 2 vectors is the component that is parallel to the direction of velocity. The other vector is the component that is perpendicular to the direction of the velocity. Likewise, the rate of change of the momentum is the sum of a perpendicular component and a parallel component. If we look at the momentum principle, we can see that the net force actually equals the rate of change of the momentum. Because of this, we know that the parallel component of the net force and the parallel component of the rate of change are equal, and that the perpendicular component of the net force and the perpendicular component of the rate of change of momentum is equal as well. Now, let's imagine that the black hole in question was removed and replaced with another black hole of a different mass. Despite this change, the positions of the star are unchanged from what they were with the first black hole. This scenario could only occur if the mass of the star was changed as well. As we can see from the equation here, if the mass of a black hole were to increase or decrease, some value on the right side of the equation, other than the distance between the star and the black hole, would have to increase or decrease as well to maintain the same distance between the star and the black hole. Thanks for watching.